we're converting the energy of hot water to kinetic energy of the air, which can then drive the turbine, which drives the generator and produces the electricity.
Globally, 50% of the world's total energy consumption is rejected as waste heat. It's a huge resource that we may untap, and that equates to reducing global carbon emissions by about 1 or 2%.
So, kia ora, welcome to Tairāwhiti. You're soon to be home.
Kia ora.
Right?
Yeah, soon to be home, moving to Gisborne next month to start building the Vortex Power pilot plant.
I'm Richard Flay, and I work at the University of Auckland, and also I'm Chief Scientific Officer of Vortex Power Systems. So I'm here as the Chief Scientific Officer today.
I'm Billy. I'm the Chief Operations Officer at Vortex Power Systems. I've got a background in process engineering and the project manager of this pilot plant that we're building down here in Gisborne.
Why here?
Well, whangara sort of stood out for us for a couple of reasons. First place in the world to see the sun, and first place in the world to see this new technology. An innovative region. Rocket Lab have obviously sort of set a precedence in the area, and the region and the community are really supportive of innovation and new technologies and working sustainably, you know. So we put a notice out to some of our investors and said, hey, would anyone be willing to accommodate a Vortex pilot on their site? And Toby Williams of Tairāwhiti Station reached out to us and said, look, sounds like a really cool project. We'd love to have you in the region and in the community. So we had whangara marae and some of the local schools up the coast here come down for the blessing. Which was really cool, and so we've got a good relationship with them, and I think they actually blessed the site as Wahoo Otarangi, which I think is Vortex of the Skies, which is a cool little name for it.
That's a cool name.
Yeah. So we're artificially creating waste heat to drive the atmospheric vortex power plant. So that will include just basically producing a lot of hot water in a hot water tank and then pumping it up through this Vortex power station. And it's essentially, we essentially pump hot water through a bunch of nozzles, kind of through a sprinkler system. The hot water heats the air, the hot air rises, and as that hot air rises, it draws in the surrounding air, and they're drawn across a gallery of swirl vanes, which give that incoming air rotation, and then you get a rising body of swirling air, which forms a vortex. And in the center of the vortex at the base, we've got a proprietary vortex turbine, which Richard has kindly designed. And the vortex will drive that turbine and generate electricity.
Can you tell us a little bit more about the intended outcomes for the company?
Yes, so globally, 50% of the world's total energy consumption is rejected as waste heat. So there's this huge resource of waste heat that's untapped because there's no current technology capable of converting low temperature heat into electricity. And that's the application of the atmospheric vortex.
So these vortices, they occur in nature. So we have water spouts above the sea and dust devils, and they occur when you have a certain combination of circumstances of warm air rising and swirl. So what we're doing with our vortex engine is providing those conditions to make it happen artificially. So we provide a ring of swirl vanes to give the swirl and the flow. We provide the hot water, which evaporates and raises the temperature of the air so it rises, and so we can generate high speeds at the base. And that's really the key advantage of this technology, is that we're converting the energy of hot water to kinetic energy of the air, which can then drive the turbine, which drives the generator and produces the electricity. I'd read an article about producing a vortex and using it to create electricity. I thought, wow, that'd be a really interesting thing to get a student to research on. And a few years later, someone came into my office and said, I'd like to do a master's degree on this project or that project. One of them was looking at a vortex. And I said, well, that's the one I want to do. And that student was Neil Hawkes, so he's one of the co-founders. And then we built the Vortex cabinet and started the company, Vortex Power Systems. And because we had the company and it was able to raise funds, we could do more work than you would normally be able to do at a PhD, because our rig in the lab is very expensive. And in that process, we also applied for a Marsden grant and we got almost $1 million. So then that could be used to fund 2 more PhD students and a postdoctoral fellow. So with those students and a postdoc, we delved into computational fluid dynamics, and that work is still ongoing. We got yet another PhD student, so he's an experimentalist, and he's measuring the flow in our vortex extension cabinet using PIV, so it's kind of flow visualization where you can really see the vortex. So it's kind of really grown, the Marsden, the Vortex Power Systems, and then raising the funds now to build a pilot plant. So it's never in my wildest dreams that I think this would happen, right in those early days, talking to Neil when he came in, quite a few years ago.
So the Vortex pilot plant behind us here should generate 500 kilowatts of electricity, and the diameter, it's a circular vortex power plant. The diameter of that plant is about 15 meters, and the diameter of the swirl vane gallery is about 35 meters. So you've got a 35 meter circle generating 500 kilowatts of electricity.
And there are very few moving parts. Like, we got the swirl vanes around the outside, so they're fixed, they would look like yacht sails. So we have the technology in New Zealand to build those.
We might have built one of those, one or two of those, yeah.
And then the moving parts are the turbine in the middle. So for here, this turbine is 4 meters in diameter, connected to the generator, and they're the only moving parts. So
it's a freestanding vortex. So we have control of the heat supply at the base. We have control on the water supply and therefore control of the heat supply.
And control of the angle of the vanes, so how much it swirls. And so the swirling flow rises to many kilometers as a sort of coherent rotating feature of the flow until it reaches sufficient height that it breaks up into a plume, and then the rotation just sort of disappears into turbulence. And we aim to create a very tall vortex. We need a tall vortex to generate the strong winds.
How tall, comparatively?
In the order of kilometers tall. So it should be a convecting core, approximately, the one we're building here, approximately 4 or 5 meters in diameter, kilometers tall. And that's what we're aiming for. The taller the better. The taller means we get more draw and we generate more kinetic energy and generate more electricity.
Because if you look at the thermodynamics, the taller it is, then the lower the temperature at the top where we reject the waste heat. And so you can kind of work out the efficiency. If you have a low temperature at the top and a high temperature or higher temperature where you're providing energy, you get a higher efficiency. So the taller we can make it, then the higher efficiency it's going to be. But also it's easy to see that if it's taller, then you'll generate stronger winds and then more power too. So it's kind of makes sense that way.
And I heard a rumour you might be going for some world records with this height.
Yeah, so I think the tallest man-made feature currently is the Burj Khalifa, but we should be several kilometres taller than that. So we may well be generating the tallest man-made feature on Earth.
that's a claim you want, right?
Yeah, it's a pretty cool claim in the Guinness Book of Records.
Book of Records, yeah.
And you mentioned aircraft restrictions, flight restrictions around the Vortex. I guess until you've proven it out, you don't know what that means in terms of changes to airspace when you start introducing it into industrial zones.
Yes, correct. So for the pilot plant, we've been very we've added orders of magnitudes of safety factors to the restricted airspace that we've attained. We hope to be able to narrow that field down significantly. So, we were able to apply for a larger airspace because we had the room to do it. So
the Vortex is locked to the Vortex engine at the ground, so the space that the Vortex is going to occupy is kind of a conical shape.
Richard's co-founder likes to describe it as if you light fire to a candle wick, if you blow on it hard enough, it leans over and then it blows out, because it's fixed to the wick. So much like that, our Vortex is fixed to the water supply, and we have complete control over that water supply. So if we want to remove its power source, we just turn it off and the Vortex dissipates. Yeah, so it's a far safer, far more controllable Vortex than you would see in nature.
Yeah, so I looked on your website and you have some pretty astounding numbers there for what could be achieved globally.
The potential of the technology. Yeah, so 50% of the world's total energy consumption is rejected as waste heat through industrial processes and power generation. So there's this huge resource of waste heat that's untapped at the moment, and actually quite a nuisance to a lot of processes.
That's right. Well, they could be an add-on to power stations, and the performance will be the highest when they're operating at full capacity. And also we'll be able to run when wind turbines aren't running. So when there's no wind, well, our Vortex will be producing power. And so it matches quite well with wind energy.
It complements the other sustainable power generation.
Obviously you're going to be linked to a waste supply or a heat supply, which means that you've got to locate near industrial areas, that kind of thing. Is that going to be a restriction to your ability to operate?
I suppose we're attaching to existing industrial sites who will already be cooling that water. In fact, the technology simultaneously generates electricity and cools their water, so they get free cooling for their process. There's another upside. And they're already pumping that water, so we both reduce their parasitic loads and increase their electricity production. So yeah, a net
in
zero.
some cases it might replace a cooling tower, and so cooling towers have big fans, so then they wouldn't require those. So instead of consuming electricity, it'd be generating electricity.
Most of these large industrial sites aren't located within urban areas, so they're sort of remote in themselves. And then you've also got people, the operators of these large industrial sites are also skilled in operating similar plants. So you've got the workforce and the knowledge already located in that area. So I think it complements those industrial sites nicely. The low infrastructure required to generate a plant of such size, or such generation capacity, it drives some really good unit economics, and I suppose if we can prove the generation capacity of it, as we suspect, we're looking to be producing electricity at the lowest cost, or as low as solar power. So it's the lowest sort of levelized cost of electricity out of all power generation.
No mining for unique earth minerals?
No, exactly.
No.
No.
Wow, I mean,
Just simple technology, a bit of some concrete, a very nicely designed turbine.
Yeah. So it's all standard technology really.
Science at its best, right?
Yeah,
Exactly.
engineering is making a complex, solving a complex problem with a simple solution, and that's what Richard and Neil have done.
So this is a trial plant, artificial waste energy. How do you go from here to the next step, and what is that?
Yeah, so once we've demonstrated the technology here and demonstrated the economics of it, we are looking to develop a commercial demonstration unit with a site partner in New Zealand. So looking for an industrial site partner to pair up with and develop a fully operational power generating plant that will either supply power back to that plant or into the national grid.
And I guess the main difference would be that here we're going to have a batch operation. So we're going to run it for short periods, and test various things. But the stage after that will be continuous operation. So we'll need a continuous supply of hot water.
Yep. Then we'll be able to demonstrate the the site partner will be able to demonstrate the commercial viability, site integration.
How many days per year we can't operate because it's too windy and things like that.
How many days we can operate it. Yeah. It would be fantastic to see more investment in New Zealand because we do have exceptional thinkers in this country and exceptional ingenuity. So it's a really good incubator country for startups and new tech and things like that. But in that same light, we have such good ingenuity that we can do things, and I think we should in some ways be proud that we can get things across the line using 10% or a fraction of what everyone else needs, Yeah.
First of all, thank you for taking me up to your site. I'm intrigued by Vortex Power Systems and what you're trying to achieve. It's just a phenomenal project. And I guess I wanted to dive into sustainable technology a little bit more and ask if, in your research capacity, this is something you're seeing New Zealand embracing. In particular, are more people taking on some of these really big challenges?
Yeah, well, it's interesting you asked that because it certainly is a trend that I've seen over my career at the university, that not only are we emphasising more on sustainability in our teaching and our research, but the students want it. And for example, recently I was contacted by a young student who'd heard about Vortex Power Systems and wanted my advice on career paths to get into clean energy. And I thought that was really exciting, actually. And the young people are, far more focused on that kind of thing than the older generations, because it's more prevalent now. They see, that we need to look after the planet. So I guess our teaching's adapted and the attitudes of students have changed. So Vortex Power Systems is contributing to all of that.
Yeah, it's been incredible to meet you both, and a wonderful project. I can't commend you more on what could be a groundbreaking project.
Thank you, Shannon.
Thanks, Shannon.
Thanks very much.